This is the general idea that we are striving for. We're trying to approximate the area above the x-axis below the curve y equal to f of x for some function f of x that lies above the x-axis and on the interval from x going from a to b. The way we do this is we take the interval from a to b and we cut it up into n equal sub-intervals, n being some whole number, and the width of each of these subintervals is going to be the same because they're equal. Specifically, it's the distance from a to b divided by n. We call it delta x, and so that's b minus a over n. It's how long each one is. We label the endpoints of these subintervals. We're going to let a be x sub 0 and b be x sub n, so that between a and b we have x sub 0, x1, x2, all the way up to xn minus 1, xn. So there are actually n plus 1 endpoints for the n intervals. Okay. To approximate this area, we can use the White endpoints, which means that for the first subinterval we use x1, the second one we use x2, the third one we use x3 all the way up to xn. We take the base, which is delta x, and multiply by the height, which is the value of the function at the right endpoint. We add those all up. And I can factor out a delta x because that's a factor everywhere, and I just get delta x times the sum of f of x sub I from 1 to n. So this notation just means I'm adding up f of x1, 2, 3, all the way up to n. If I use the left endpoints, then I start at x0, and then I use x0, x1, all the way through to xn minus 1. So it's almost the same formula, but I start with x0 and I end at xn minus 1. Using the sigma notation, it's the sum from 0 to n minus 1 of f xi, all times this factor delta x. More generally, we can choose sample points, which I'm writing by x star. And so x1 star is a random point from the first subinterval. x2 star is a random point from the second subinterval. x3 star from the third subinterval, etc., all the way up to xn star, which is a random point from the nth subinterval. Then I can take delta x times f of x1 star plus delta x times f of x2 star, etc. The delta x is always the same. It's just here I'm determining the height by the value of the function at a random point in each subinterval. But again, I can factor out the delta x, and I'm left with delta x times the sum from 1 to n of f of xi star, and these are my approximations. This is how you do it. And the really big, broad, overreaching idea is this. The area that we're looking for is the limit as the number of subintervals goes to infinity of the approximation for that many subintervals. If the limit exists, great. That's what we want to call the area. And it works with the circle, it works with that parabola example we looked at, and generally this is going to work for everything. However, this approximation way of trying to calculate things is absurd. It's fine for calculators, but for you and me, we would like a better way to do it. We'll see that there is. So in motivating integration, first we talked about the area problem, which is really, in a sense, the counterpoint to the tangent problem when talking about derivatives. And it's not necessarily clear how that is the case. However, another way of motivating the derivative is to talk about the velocity problem. Given a position with respect to time, can you find the velocity? And, well, yeah. The inverse problem to that pretty clearly is the distance, or I suppose position problem. Given speeds or velocities, can we recover the distance traveled? So the velocity problem is starting with the position, getting to the velocity. This problem is starting with the velocity or speed, getting to the distance or position. So for example, let's say I'm taking the BQE from the Verrazano to the RFK bridge. I check my speed about every 5 minutes and I observe the following. Okay, so here's the deal. As I'm going from the Verrazano to the RFK bridge, I pass some landmarks. After 5 minutes, at first I'm at the Verrazano bridge, landing in Brooklyn, Fort Hamilton I guess, and I'm going 45 miles per hour. After about 5 minutes, I've reached the beginning of the Gowanus Expressway, and I'm going about 30 miles an hour. 5 more minutes and I've hit the Prospect Expressway and I'm zipping along at 50. Then 5 minutes later, I'm at the Brooklyn Bridge and I've slowed down to about 35 miles an hour. 5 minutes later, I'm at the LIE and I'm going about 40. 5 minutes later, I have either the option to get onto the Grand Central Expressway or continue to the bridge. I'm going about 45. And finally, I reach the bridge and I'm going down at about 35 again. So these are the speeds that I've looked at. Now what I can do is I can estimate how far I've traveled over each time interval by using the speed, either say at the beginning of the time interval or the end of the time interval, the left or the right, to estimate how fast I was going over that entire time interval. So for example, for the time interval between 0 and 5, I can assume I was going 30 miles an hour for 5 minutes. Or I can assume I was going 45 miles an hour for 5 minutes. So either, since 5 minutes is 5/60ths of an hour, I either traveled 5/60ths times 30 or 5/60ths times 45. That's my approximation at least. So I do that. 5/60ths is going to be the time interval for every single one of these things. It's 5 minutes divided by 60 minutes per hour gives me 5/60ths of an hour. I multiply for the first guy against 30 plus 5/60ths times 50, and then 35, then 40, 45, 35, to get this expression right here. My approximation there is 20.42 miles. Or I can use the speeds at the beginning of each interval, which is the left endpoint type of approximation. So I get 5/60ths times 45 plus 5/60ths times 30, etc., 50, 35, 40, 45. I add those together and I get 19.58 miles. So this is how I can use this data to estimate how far I've driven. I guess maybe my odometer is broken, but my speedometer is not. I don't know. I also could have gotten a better approximation if I were checking the speed more often, but I suppose the more time I'm spending looking at my speedometer, the less time I'm spending looking at the road, and, you know, what's more important? Anyways. So generally, this is the solution to this idea of the distance problem. We have n time intervals of length delta t. On each time interval, we have a speed with given by f of t sub I star. This is just meant to indicate that this is some random time in the middle of the ith subinterval. And then the distance is approximated by the length of the time interval times the speed. That gives me an approximation of how far I've moved over the first time interval, the second time interval, etc. I add those all up, and this, again, looks like something delta t times the sum from 1 to n of f of t I star. This looks almost, well, pretty much precisely like the general approximation for the area under a curve that we wrote before, except I had x's here instead of t's. But it's the same thing. This is what should suggest that the distance problem and the area problem have a lot to do with each other. Also, the distance problem is clearly sort of doing the velocity problem backwards. Whereas the velocity problem says start with the position, let's get the velocity. This is saying let's start with the velocity, let's get the position. So this is the first hint we have that the derivative, which has something to do with velocities, is related to this distance problem, which is related to the area problem. So the area underneath the curve should somehow be related to the derivative, is what this discussion is maybe suggesting, and that's the idea we want to have in our head as we continue.